All right, so we're back here continuing to talk about fluid mechanics. And in the last videos, we talked about uh, differential manometers and how you can analyze those. Those get into a little bit more complicated problems, maybe more complicated than ones we've done so far. So we're going to continue here. So differential manometers measure the pressure relative to different points within a fluid. We also might want to know the atmospheric pressure. If we want to know the absolute pressure, we need to know the atmospheric pressure in addition to the gauge pressure that we would get from a manometer. Okay, so a device that we use to measure the atmospheric pressure is called a barometer. And so the atmospheric pressure is sometimes called the barometric pressure. So a manometer and a barometer both measure pressure, but a barometer is atmospheric and a manometer is going to measure the differential pressure or maybe the gauge pressure. Okay, so we're going to keep those straight. And a barometer, the most common method that is used, it's really similar to a manometer actually because it's based on this idea of fluid statics. And so we measure the height of a column. So here's like a kind of a free body type diagram you can use to understand this. So here you've got a fluid inside of that one, and you have a cylinder that you lift. And when you lift it up, you've got the atmosphere pushing down, and then we've got this little vacuum that'll form above it. So here the pressure is like zero effectively. And then the height of this fluid has to be counterbalanced by the force pushing up on it from the atmosphere. So the atmosphere pushes down on the surface of that one, and that then pushes up here to cause this fluid to rise, okay? Because the pressure is zero at the top, it has to be bigger at the bottom. And then the height of that we can use to estimate the atmospheric pressure. So rho GH is going to be the pressure associated with this drop is zero at the top, and then we know the pressure at the bottom, and that's got to be equal to the pressure from the surrounding atmosphere. So P atmosphere is equal to rho GH or gamma H. And so we often use mercury for this because mercury is really heavy, and that means you don't have to lift this very far. And so yeah, about 30 inches of mercury is about equal to atmospheric pressure. So you only need a tube that's 30 inches tall. If you were to use water, it would have to be 30 meters tall. It would have to be very tall. So it's not practical to use water. So you want a fluid that's very heavy, and that makes it easier to measure this. So we use mercury commonly for that. Okay, so quick example where we look at that using that information. So what's the atmospheric pressure if the barometric reading is 740 millimeters, or here this is in inches, but we could do it in inches or in millimeters. So here we have the H is 740 millimeters. We're going to need the density for mercury to get the specific weight, so we could either use this version or that one. Here I'm going to use rho again, but in the future we're going to more commonly start using gamma. So rho is 13,600 kilograms per cubic meter if we go look that up in our supplemental file, and then the gravity constant is 9.81 meters per second squared. Okay, 9.81 meters per second squared, and so then we can get the atmospheric pressure is rho GH or gamma H if you do it that way. And so I'm going to write it out because we have to do a little bit of unit conversion. So rho 13,600 kilograms per cubic meter, G 9.81 meters per second squared, H is 740 millimeters, and then so I've got millimeters and then meters, so I need to convert, so I'll convert this to meters by dividing by 1,000, and then I want this in pressure units. So the units we use for pressure are pascals, which is Newton per square meter, or for atmospheric pressure we would often use kilopascals, because in pascals you would get a really big number, and so you get a more reasonable number in kilopascals. So we need to convert this whole mess to kilopascals then, and so we're going to want it in kilopascals So a kilopascal is equal to 1,000 newtons per square meter. Okay, I could have done pascals and then to kilopascals, but here I'm kind of skipping a step. And then I've got newtons now, and I haven't got that over there. So to be perfectly correct, we should also include that a newton is a kilogram meter per second squared. So this should make all the units work out. So I want that one. Looking at kilograms and kilograms, those cancel. Second squared. Millimeters already did. So I've got meters to the fourth up here, and then meters to the fourth down there. So all the meters will go away. Okay, and then the newtons will go away, and so it leaves me with kilopascals, and I get that the atmospheric pressure here is equal to 98.5 kilopascals. So a little bit less than you would see at sea level typically. All right, let's stop there, and then we'll do one more.